So we're going to define this a little bit. We're going to define this more in the next class. But there's this topic called concavity, which I'm hoping that you've looked at before. But for something to be concave up, it has this general bowl shape, and for it to be concave down, it's the reverse. And let me draw that in a different color. So here's concave up, here's concave down, and we can think about our function. You know, here it's concave down, and then at some point it's switching to be concave up. And one way that I've heard of concavity being described, which is helpful, is, you know, if you put water into something that's concave up, if you put water into here, it would stay, whereas if you put water into here, it would fall right out. So that's just one way to think about that. I mean, you could think about, you know, water dripping into here, and it's going to stay, whereas water, if it were to be put in here, would just fall right out. Okay, so we're gonna need to have that definition or that understanding of concavity for this question. What happens when the derivative is a maximum or a minimum? Either one. Well, if we think about that, you know, here's my derivative function, and here's my function. When my derivative has a local, in this case, minimum, remember, you know, this is x, and this is f prime of x. As we go down this graph, you know, in this whole blue range, we know that f prime of x is less than 0, so my function is decreasing. And, you know, as we connect each x point to its corresponding y value, or corresponding f prime of x value, this point, the minimum point right here, the minimum point right there is where f prime of x is the most negative. And remember, f prime of x, that's where the tangent line has the most negative slope. So if we think about that in terms of our function, you know, up here, it's where my tangent line is going to be the steepest in the negative direction. So when the derivative has a maximum or a minimum, that's when tangent line is the steepest. And what else is going on? Well, that's also the point where I'm switching my concavity. So at that point where I have the minimum, you know, if I were to draw a line straight up, so just drawing this line straight up, that's where my function goes from being concave down to concave up. So what happens when the derivative has a maximum or a minimum? Well, one, the tangent line is the steepest, and two, you switch concavity. And we'll talk a lot more about this, but that switching of concavity is defined as the point of inflection. Make sure you write this down, put it in your notes. We're just referencing it right now, but I'm expecting you to be familiar with this definition, the point of inflection. And so the point of inflection right here is when we switch concavity, and that's when the tangent line is the steepest, and that's when our derivative has a maximum or a minimum. Okay, so let's look at another function and answer these questions. Again, what is always true when the function is decreasing? So let's just, here's f of x, here's a point where it's decreasing. We said when f of x is decreasing, we expect that the derivative function should be less than 0. Is that true? Well, looking at the corresponding values, it is in fact below the x-axis. So cool. What is always true when the derivative is 0? Well, what we said is, you know, when f prime of x equals 0, we're going to get a local max or min. So let's look at a couple of points. Here it's 0, and there's local min. Here it's 0, and there's local max. So our rules are holding. question. What's always true when the derivative is positive? Well, we said when the derivative is greater than 0, or when it's positive, our function is increasing. So let's look at that to make sure that it holds true here. Here's a section where my derivative is positive, where it's above the x-axis, and it corresponds to this section of my function graph where the function is increasing. What happens if the derivative goes from positive to 0 to negative? Where does that happen? It happens in more than a couple places. It happens here, and it happens here. Again, we're looking at when the derivative is above the x-axis, or it's positive, it equals 0, and then it's negative below the x-axis. And that corresponds in both cases to local maxes in my function. So when the derivative function goes from positive 0 to negative, the function has a local max. Last case, when my derivative has a maximum, what is happening with the function? So, and maximum or a minimum, but right now let's just look at a maximum. So here my derivative, here's my function. So here my function has a maximum, and if we go up from there, what we expect to happen from what we looked at before, if the derivative function has a max, we expect that the f of x has the steepest tangent line, and at that point it's changing concavity. And just as a definition reminder, that's called the point of inflection. So is that in fact true? Well, if we go to where my derivative has a maximum, up here, this is the steepest point. And if we look at the concavity, here we're concave up, then we switch to concave down. So those rules hold true always, and we just looked at two cases where they're holding true. So this is just a picture to think about the derivative function's relation to the function. So how does f of x relate? So how does f prime of x, how does the derivative function relate to f of x? So we said, if the derivative function is greater than 0, on some interval, between a and b, so here's a to b, then f must be increasing on that interval. F must be going upwards. And if our derivative function is less than 0, so if the slopes are negative, then my function must be decreasing on that interval between a and b. So this is just a more formal way of writing what we've already looked at. All right, so here's a nice little picture. Here's my function. Here's my derivative. And just to pool in some important ideas that we had. Here on if I look at my derivative function, I've got a positive slope, 0, negative slope, and what does that correspond to? Well, that corresponds to a local max. So a local max on the function corresponds to positive, 0, negative on my derivative function. What else? Well, here at C, I have a local min of my derivative function. does that correspond to on my function itself? Well, that corresponds to a point of inflection. So here we have point of inflection. And the last case, at point B here, we've got a negative slope, 0, positive slope. So negative, 0, positive for my derivative function, and that corresponds to a local minimum for my function. So we've got three major things going on. First one, if the function has a local max, that means its derivative is going positive, 0, negative. If there's a, so second thing, if there's a point of inflection, so where the concavity changes, that means that my derivative must either have a minimum or a maximum. And then the third major thing, which is right here, if I have a local min on my function, as I do right there, that means that my derivative function must be going from negative to 0 to positive. And we need to define something that we've been really using so far, but we haven't given it a formal name, which is critical number. And a critical number is a value of x that makes f prime of x 0 or undefined. So we'll be looking at critical numbers throughout the next couple weeks. But critical numbers, where are they? Well, critical numbers are a value of x that makes f prime of x 0 undefined. So our critical numbers here would be a and b. So now let's look at what a homework question might, a class time question might look like. Gives us a graph of G, and we want to answer questions about critical numbers and the derivative function. So where does G have critical numbers? Remember, critical numbers, where the derivative is 0 or undefined. Well, that's going to happen there, and there, where the tangent line has a slope of 0. So where does G have critical numbers? At x equals negative 2, 0, and 2. Okay, on what intervals is G prime negative? Let's just answer the negative, not the positive. Where is G prime negative? Well, G prime is negative when f of x is decreasing. So where is f of x decreasing? Here and there. So the intervals are from negative infinity to negative 2, union, or including, 0 to 2. And notice that I'm using parentheses, meaning it doesn't include those endpoints. Because at negative 2, it's neither decreasing or increasing, it's 0. And at 0 and 2, it's neither increasing nor decreasing. At that point, the slope is 0. All right, I'm going to answer C and D on the next video. This is a longer lesson, but critically important, so really stay focused with this.